Null hypothesis significance testing, or NHST, is again under fire in psychology and related disciplines. Several movements have sprouted to put an end to NHST once and for all. And one of these movements is Cummings' The New Statistics. However, although NHST should disappear, it is not for the reasons given by Cumming. That is, after all, NHST is a bad theory. It is an incoherent mishmash of three other theories: Bayes, Fisher, and Neyman-Pearson's. So when Cumming uses this mishmash, he's weakening any sensible argument that could be gained from using the original theories, while at the same time he's risking promoting pseudoscience within psychology. Now, this is a snapshot of Cummings' argument. Actually, is the figure 1 that he used in his 2014 paper in Psychological Science, and it goes something like this. Okay, simulate an environment, for example, that of two populations with a medium effect size between them. Set an alpha level of, a conventional one of 5%. Take random samples of reasonable size from each population and test their differences using a t-test for independent samples, and then run the simulation, for example, 25 trials, and see what we can conclude from there, right? And this figure 1 in his paper, is represents a result of such a simulation. So Cummings' arguments and conclusions are the following. He says, if P, the p-value reveals truth, then replication P's could vary slightly, but not by much, okay? Yet, if you look at the p-values, they are all over the place, ranging from p-value for smaller than 0.01 to as high as 0.749. So, practically, he says p-values can take any value you may think of, and they are rather unpredictable. So, p-values are not dependable. Now, if you look at confidence intervals, you can expect them to dance around, but yet you also expect that the effect size in the population, the difference between the groups, for example, will be captured 95% of the time. And indeed, if you made the calculations in this simulation, 92% of them did, which is, is a pretty good match given the small simulation. He also says, well, we don't do repeated sampling, we just do a research. So this is equivalent to choosing randomly from an infinite sequence of replications. So a single confidence interval is informative about such infinite sequence because it tells you where you can't reasonably expect the population mean to be, right? But a single p-value doesn't. It just simply is all over the place. Therefore, he concludes, confidence intervals are more informative, tell you more about replicability, and they are more dependable than p-values. Therefore, we ought to substitute them in psychological research. The problem that I have here is that Cumming is using NHST for his arguments, and this is tripping him up. Alright, so let's look at it in more detail. Now, repeated sampling from the same population makes for good simulations, but it doesn't represent well the way the majority of testing is done in psychology. And even when it's done under the rubric of NHST, it is closest to Fisher's approach than to Neyman-Pearson's approach. But let's start with that later, right? So one of the main features of Neyman-Pearson's approach is that it is based on known population or assumed known population. So you can provide a specific alternative hypothesis to the test. For example, in this case, that the difference between the population is as a medium effect size, right? A second feature is that because there are two hypotheses, the test trickles down to a decision between the hypotheses. And the decision is that either the main hypothesis or the alternative hypothesis explains the research results better. Now, this decision is based on reducing a type 1 error or the alpha probability. And in this case, p-values really are not necessary for making that decision. You could use them as proxies though, but what is important is to know, in this case, at which end, or like which side of the alpha level the p-value falls. The actual value of p, how far away p is from this alpha level, is irrelevant. All right. So we can clean this up, and so to better represent Neyman-Pearson's approach, so we can reduce p-values to just showing locations regarding in relation to alpha, and we can take the lower limit of confidence intervals for illustration, so removing the rest of the interval, right? Now, using the same parameters that Cumming used in the simulation, and for an alpha level of 5%, we can expect that a power of 50% for this simulation. That is, that we expect 50% of the tests to show a p-value greater than alpha, 50% of them to show a p-value smaller than alpha. And what do we get here? Then we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 tests with a p-value smaller than alpha, which is actually a posteriori power of 48%. Pretty much what we expected. Now, keep all other parameters similar, but move alpha, make it 1%, and consequently the level of power will decrease, in this case to 26%. But again, if you count the tests that whose p-value is smaller than alpha, you will get that 28% of them are explained by the alternative hypothesis. And if you go the other way and move the alpha level up to 10%, again you find that the observed power is very similar to that expected. So what we can conclude from here is that under Neyman-Pearson's approach, Cumming simulations behave as expected, given power, right? So random sampling from the same simulated environment captures the alternative hypothesis as expected. That the exact p-value, and therefore its stance, is irrelevant under this approach, and that confidence intervals may be more descriptive, but they do not perform any better when testing research data. Now, we can also look at the same results, the same simulation results, from Fisher's perspective. And the first thing that we need to understand here is that under Fisher's approach, there is no explicit alternative hypothesis. So there is not knowing the effect size in advance, and there is no way of controlling power either. So a simulation based on repeated sampling from the same population does not actually fit this approach. But still we can learn something from it. So let's continue. Okay. So a second aspect of Fisher's approach is that the p-value, because we only have one hypothesis, the null hypothesis, and rather than two to make a decision between them, the p-value plays an important role as evidence against this null hypothesis. And of course, the smaller the p-value, the more confidence we can have when rejecting the null hypothesis. Therefore, the exact value of p is important under Fisher's approach. And as Cumming shows, if we plot the location of p-values around a conventional level of significance, for example of 5%, we see that they dance around, they are widely dispersed around this level of significance. But the question is, so what? I mean, there's no reason why p-values ought to be limited to a small range, even if they are taken from the same population. Furthermore, there's no reason why, as Cumming says, confidence intervals are free to dance, but p-values are not. I mean, both are actually statistics taken from the same samples. So it is the samples that dance, and the statistics are logically allowed to dance in the same way that the samples do. And indeed, we can see that if we plot the p-values again, for example, for like the point estimate of the confidence intervals, and here we see that they dance together. I mean, they come from the same samples, therefore they dance together. Again, there is no logical or statistical reason to applaud the dance of confidence intervals, but at the same time criticize p-values for doing the same. Furthermore, regarding future predictions, a confidence interval is a wide net, and with a wide net you can catch a lot of fish. So this may correlate with the next confidence interval, but has nothing to do with prediction. So this actually means that given the dance of the samples, there is no reason to expect a p-value to predict future p-values in the same manner that we cannot expect a sample to predict future samples, even more so when the underlying population effect size may not be known. So we ought to conclude that also Fisher's tests behave as expected, and that alternative hypothesis not being known makes random sampling from the same simulated environment inadequate for testing this approach, which, by the way, is the most common in psychology, that the dance of p-values is expected, and that it correlates with the dance of confidence intervals, and that, again, confidence interval may offer a more descriptive information, but they are not expected to perform any better than the alternative, that the test when the alternative hypothesis is unknown. And with this we come to our main conclusions. So Cumming knows that NHST is an incoherent mixture of the theories of Fisher and of Neyman-Pearson. And still so he uses it. I don't know, perhaps because he thinks that is what most psychologists use, so they are more familiar with, or perhaps it's because otherwise he wouldn't have an argument. But using a bad theory to argue a point is bad practice and leads to pseudoscience. So, as I hope I have shown here, confidence intervals are not better than Fisher's or than Neyman-Pearson's theories when appropriately compared, although we may agree that they are certainly more descriptive of the research data and therefore more informative. So yeah, in summary, Cumming is right in advocating confidence intervals, but his argumentation against proper data testing techniques is unfortunately based on bad theory. The main recommendation is ditch NHST because not only is pseudoscientific, but it will trip you, it leads to confusion. And if you have to, use Fisher's or Neyman-Pearson theories, instead of NHST, but as well for testing data if that's necessary. And with basically this is all what I have to say. If you want to know more, there are some references here, and I hope that you enjoy this presentation.